to study cosmology. All right, in December, Christine Chen will be talking about debris disks and the evolution of planetary systems. Yet another one of the hot topics in astronomy, talking about extrasolar planets and how planetary systems develop. I mean, I remember when I was a wee lad, just an undergraduate, we knew nothing about how planetary systems develop, and the amount that we know now is just amazing. It's one of the great topics. Unfortunately, in January, we have our favorite speaker, TVA, because it's hard to get somebody just after New Year's. I wanted to ask a question, folks. Would you prefer that we delayed this until January 10th instead of January 3rd? Or would that not make a difference? Anybody think it would be good to delay? Anybody okay with? Everybody would just think the 3rd is better? And who doesn't really care? Okay. Overwhelming don't care a little bit towards the January 10th, because the American Astronomical Society meets the first week of January, and I often have trouble getting speakers because half the institute is out at the conference. So I might consider delaying that. All right. The construction update. Hopefully you guys had to come a different way to get here. Hopefully, obviously you made it. Hopefully there isn't another 50 people out there getting lost. If so, hopefully they will find their way in. You have to come from the south because north of it is closed. Here is the map. This blue part is the stuff that's done. Looks real nice, especially this path along here. It's a really nice little path if you see it when you're during the daylight. But this yellow section here and this red section up here, those are now closed and will be through December, okay? So for the next several months, you'll have to approach from the south. It definitely has lengthened my commute. Our website with information is if you just take your favorite search engine and look for Hubble Public Talks, you'll find it. We have links to our live webcasting, both on YouTube and on the STSCI webcasting site. Our archives of the past lectures, again on YouTube and the STSCI webcasting, and a feature that has been used an awful lot because I get an email every time it is used, people signing up for our announcements. Thank you all for signing up. It makes my job a lot easier in getting the information out to people, not only around the Baltimore area, but across the country. We also, of course, have our list of upcoming lectures. So visit our website to find all that wonderful information. Announcements, well, just use our website because there is mail list at stsci.edu, but it's much more difficult. Just use our website. If you want to contact us, you can send an email to publiclecture@stsci.edu, ask comments or questions. We are also on social media, Facebook, 2 Twitter accounts, Google, Pinterest. I will note that my Hubble's Universe Unfiltered blog on Hubble site is getting updated more frequently. We have, it's the new fiscal year. The funding for this fiscal year has enabled me to put more time into my blog. I put up 3 posts last month. I also do Facebook, Google, and Twitter every now and then. I don't promise to be daily or at all on something like that. Observatory, I didn't check my email late this afternoon. The person from the observatory is obviously not here. Remind me to ask again at the end to see if they are here to take us up to the observatory tonight. Okay. And now news from the universe for October 2016. Our first story, lovely plumage on Europa. How many of you recognize the phrase lovely plumage? All right. Oh, not that many. Uh-oh. This isn't a reference for this audience. All right. This is from the Dead Parrot sketch of Monty Python's Flying Circus, where John Cleese's customer comes in to return a parrot that is dead, and Michael Palin, as the shop owner, tries to refuse to acknowledge that the parrot is dead, saying, "Oh, the Norwegian blue, lovely plumage." And just talks about how it is, it's just resting. It's pining for the fjords and such. This is an extremely famous sketch amongst Monty Python fans, so much so that when Monty Python had a reunion in London, it was celebrated with a 50-foot dead parrot by the Tower Bridge. So lovely plumage has very little to do with this story. I just wanted to show this image. But the plumes on Europa are these. And they're not really quite so lovely to look at. Matter of fact, you may not even see them unless I put in the arrows, okay? All right, so this is an image of Europa from the Galileo mission. It's a mosaic put together. And these are the plumes down here in white. The background is from the Hubble STIS instrument, okay? And you're seeing this white stuff down here, and it's kind of pixelated and stuff. And I wouldn't call it lovely. They're kind of ratty, except there is a really lovely science story behind it. So let me explain the science behind it, and you'll see how beautiful they really can be. So this is Jupiter's moon, Europa. It's the smallest of the 4 Galilean moons, okay? And we believe its interior structure has an iron core, metallic core. It has a rocky section, and then it has an liquid water ocean and an icy crust, okay? Due to various measurements in the magnetic field motion to it, we believe there is a liquid water ocean subsurface on Europa. The question is how thick is this ice layer? Is it 10 kilometers thick or is it 100 kilometers thick? We're not exactly sure. There are 2 camps that argue about this. But when we look at Europa's surface, this is Europa's surface, we see a modeled ice sea surface. And this is the famous ice rafts picture taken by the Galileo satellite, which looks a lot like the broken ice structures around the North Pole, okay, on Earth, indicating that there might be the same sort of motion of, perhaps not on top of a shallow water layer just underneath as we have here on Earth, but that there might be softer ice and there's some sort of motion, there's some breakup and motion through it, okay? We have evidence of motion of sort of ice tectonics on Europa, and it's something like this, where we've got these subsumption bands here. What we believe is happening is the cold outer ice shell is actually subducting, just like the plates subduct on Earth, subducting below another ice layer, all right? And so this is denser, and it drops down into the deeper, warmer ice, okay? And notice that they call this the convecting portion of the ice shell, all right? We sort of think of ice as rigid and fixed, but on Europa, there actually is motion through the ice, and they talk about it convecting, with the liquid ocean being underneath that ice layer. Again, how thick is this ice layer? We're not sure. So it shows there is at least motion in the ice on Europa, and there's water deep underneath, and the question is, well, how much of that water gets up near the surface? Because if we want to check for life in the universe, we need 3 things. We need energy, carbon, and water. That's what life as we know it requires. Well, energy and carbon are pretty easy to find. Water is really, really hard to find. So Europa, where we know there is some water, is a place to look to see if life could have developed, even microbial life on Europa. All right? So we have actually seen water plumes on another moon. This is Saturn's moons Enceladus. By the way, this is Saturn's rings up here, okay? A nice edge-on view of the rings. And this is from the Cassini satellite, where you can see these plumes coming from Saturn's moon Enceladus, all right? And we've also seen indications of possible plumes on Europa from Hubble. Now, Hubble did not see water plumes. This was in 2012. What Hubble instead saw was auroral emissions from hydrogen and oxygen. What is water composed of? H2O, hydrogen and oxygen. So these are auroral emissions associated with Europa from hydrogen and oxygen, which are indicative that there might be water plumes. So how are we going to look for them? Well, we're going to be tricky, and we're going to look for them as Europa goes into transit in front of Jupiter. That way, we get the bright background of Jupiter in order to back illuminate Europa in order to search for these plumes. So here are the actual images from the scientific paper as submitted. All right, so this background here is Jupiter. This is Europa. And here are some evidence of plumes. Here's another image. Again, here's Europa. Here's some evidence of plumes. As I said, they're not pretty to look at, but they indicate a really interesting story, that there might be water plumes spewing out of Europa. And we can then examine that water to see what is going on, what is the chemistry, what is the details of what may be going on in this internal ocean, which, if it's 100 kilometers deep, below 100 kilometers of ice, is going to be really hard to get down to, okay? If you want to drill down 100 kilometers to get to the liquid water ocean, that's quite an engineering challenge. If it's 10 kilometers, well, I think that's a little bit easier. It's still quite the challenge. If, however, that water vapor is spewed out from the surface, that's much, much easier. So this is an exciting announcement. It is not absolutely 100% confirmed that it is water plumes there, all right? But it does look like that there are water plumes coming from Europa, and we will continue to study and have more information as we go. This is an exciting idea of where we're going to look for potential life in our solar system. Our second story, a smashing finale. If you were here last month, I talked about the Rosetta mission and the Philae lander that is in orbit around the comet 67P Churyumov-Gerasimenko. All right? Yeah, that's quite a mouthful to say. All right, and Rosetta is a mission that started in 2004. It's been going for 12 years, okay? Most of that time was spent in a very circuitous bunch of orbits just to get out to match orbits with the comet. Matter of fact, it did a whole bunch of flybys in that process. So it launched in March of 2004. It flew by Earth in 2005, Mars in 2007, Earth in late 2007, the asteroid Steins in 2008, Earth again in 2009, the asteroid Lutetia in July 2010, and then spent 4 years matching orbits with Comet 67P CG. When it got there, it found it was a contact binary comet, which of course earned it the nickname Comet Rubber Ducky for obvious reasons. It has then, since then, since its arrival in August 2014, the Philae lander was dropped down on November 2014. It stayed with the comet through its perihelion passage, its closest passage by the sun, which is generally the most active time for a comet, right? As it goes by the sun, most activity is going on there. And it stayed with it for another year later, and the mission ended last Friday, September 30th, 2016, with a very slow crash landing on 67P CG. Now, you may remember that Philae landing was quite an event. It was the only scientific event I know of that had a live blog by a webcomic, XKCD. The author of XKCD drew over 100 different pictures to live blog the landing of Philae over the course of several hours as it was going. So you can see here's the one I chose from time until landing, 3 hours, and he has all sorts of fun information and makes some good science jokes. If you don't know XKCD, it's a very, very geek comic. Okay, so if you want to grow up to be geeks, guys in the front row there, okay, you got to start reading XKCD. All right. The Philae lander, however, didn't happened the way it actually bounced the rockets that were going to the anchors that were going to push into the comet didn't quite work, and it was lost until, as I showed you last month, it was found in this little crag here. The Philae lander was finally discovered as the Rosetta orbiter got close in enough to actually see and search for it, and found it. So there's the last resting place of Philae. Of course, the Rosetta orbiter itself joined it last Friday. But what I remember most about this mission is not going to be these images I'm going to show you in a minute, but really the number of really cool outburst images that Rosetta was able to get, because it stayed with the comet for a year before perihelion and a year after perihelion, covering this active time in the life of the comet. You can see all of these outbursts it was able to capture. This is an immense data set that we will look at for years and even decades to come. Yes? That was in the Wall Street Journal. The Wall Street Journal covered the outburst, because this is one of the great montage images. Well, I'm glad to hear the Wall Street Journal covers great science, because this is an amazing amount amazing amount of observations compared to what we've had in terms of covering outbursts on comets. Okay, and this data set will be mined for years to come. Okay, so they took they released 15 images of the descent of Rosetta over the last 24 hours. So in the lower left, this is the time to impact, 23 hours, 30 minutes for this first image. And here's the height above the center of the comet, 22.9 kilometers, or I guess height above the surface of the comet. And this is just a counting number, so I can keep track. Downloading 15 images and keeping them in the correct order is not that easy. All right, so here you can see that a day before, it's still, you're seeing pretty much the comet. You got a full-size view of the comet, and you can see it's orbiting around the comet, and the comet itself is turning, the comet nucleus. And as we start to get in, now we're down just a little bit closer at 20 kilometers. And also, these images go from the wide-angle view to the narrow-angle view here. You can start to see that, you can see the very craggy surface, almost feels like it's sharp, okay, surface. Moving in, you can see the sort of steps across there, really interesting structures. And then you've got a series of couple images where you can see the same structures. These are just relatively close in time. You can see that structure here, and you can see the structure is moving through here. Then we get what I think is the coolest image. So we've been looking down on this. Then we get this image, which looks like you're down on the surface of the comet, right? But what it has to be, because you're 16 kilometers away from the comet, this is the narrow angle camera, right? But what it has to be is, whoops, let me go back, is that you're looking at one of these crags here from the side. Okay, so as it orbits around the comet, it's looking directly along here, and you're looking in to see these crags sticking up. And I actually think this is the coolest image of all this series of 15, because it just sort of gets you a feeling like you are there. You almost feel like you're walking on the surface of the comet nucleus. So this is kind of fun. It looks a little bit like there's a national park in the Southwest. Bryce Canyon, that's it. Bryce Canyon has a little bit of the hoodoo feel of Bryce Canyon National Park. But Bryce Canyon doesn't look that rocky in that case. Anyways, so there is no erosion, right? Exactly. You couldn't have real hoodoos here because those are produced by water erosion creating them. All right. I'm not an expert on this, okay? Matter of fact, I'll show you how much I'm not an expert, because they've got a couple images here that I'm not exactly sure why they look like this either, okay? And then you can see, as we're getting closer, we're 9 hours before impact, okay? and then we jump to almost 6 hours before impact. And here you can again see these sort of striation structures, okay, which to me look like sedimentary stuff. And I know it's not sedimentary stuff. Maybe it's produced by the collision of those two contact binary objects that form the contact binary. So you've got this sort of striated stuff, and then you get this sort of leathery type plane here, okay? And we have a lot of this type of plane that we're zooming in. We're now 3 hours before impact. All right, okay, moving in here. Here is the target area for where they're going to land it. You can see that cliff along here, 3 hours before impact, 6 kilometers above the surface, down to 1.2 kilometers. You can see an edge with this very sharp shadow here. All right, you're seeing the details. And then the final image, 1 minute before impact. This is from 20 meters height. I'm told this is about 1 meter across on the comet. So it's out of focus because the cameras were never meant to focus 20 meters away from it. And then, boom. The Rosetta signal was lost at 11:19 GMT. Here is the signal, and there is not. Okay? So the Rosetta mission will live on through its amazing data set. When I tweeted about this, I said, Rosetta is dead, long live Rosetta, because it really will have an amazing impact on cometary science. However, it will not have the kind of impact that people talk about in Hollywood movies. So I'm going to give the last word to XKCD, who put out a Rosetta comic on Friday. You can read it for yourself. And it references the movie Armageddon, in which they did try to blow up a comet to deflect it. This was not meant to deflect the comet. Bruce Willis was not required on the Rosetta mission, okay? Any questions for? Yes. Okay, so as the comet approaches the sun, it heats up, and any pockets of volatiles that are near the surface can go from their iceous state to gaseous state and blow out as jets. That's very common on comets. Matter of fact, what you're looking at with the 67 PCG mostly is the comet nucleus. Okay, but what you usually think of of a comet is this big fuzzy ball. Well, that's the coma. That's all the gases that have come out from the comet, all right? And then you get those gases get swept back into a tail, all right? And that's what produces your standard idea of a comet. What we're studying here is really the comet nucleus, and those outbursts are the gases that are bursting out. The perihelion for 67P is only 1.2 times the Earth's distance to the sun, so it never gets really close to the sun. Therefore, it doesn't burst out that much, and it doesn't produce a coma. It's a short period comet. It only has a 6.4 year period, so it doesn't develop the big long tail like you may have seen with Comet Hale-Bopp, or the way we depict Comet West or Comet Ikeya-Seki or other of these spectacular comets. This is just your normal, ordinary, run-of-the-mill, boring comet. Sorry, most comets are actually kind of boring. They are that ice ball nucleus with the jets coming out, and not these big, huge tails that stretch for millions of kilometers. Good question. Thank you. Yes? It's ice and rock. It's ice and rock. We usually think of them as ice balls, but we actually know, yes, they are ice and rock. Yes. Could be. It does look a lot like rock scatter. And you'll expose my ignorance on the cometary surfaces. We've never seen cometary surfaces in that incredible detail. We actually, with Pluto last year, and the Deep Impact mission that we did a few years ago, and we are learning so much, and actually what we're seeing on Europa as well, we're learning so much about ices and how they behave out in the solar system. We're just seeing, cryovolcanism on Pluto, the cryotectonics on Europa, and so how these ices interact is something that's actually pretty new. And I think it's a quite an interesting field that has developed lately. All right, I have to get to Bill's talk, otherwise we'll be here way too late. All right, so let me go to our featured speaker. And our featured speaker tonight is Bill Blair from the Johns Hopkins University. And it is Johns Hopkins. Make sure everybody in Baltimore knows that, okay? Bill has been there, and he told me, since 1984. And I was like, he doesn't look old enough to have been around since 1984.
I was a teenager.
Yes, he got his PhD at 12. He has worked on several major instruments. The Hopkins ultraviolet telescope that flew on the space shuttle twice. We had hoped it would fly a few more times on the space shuttle. And then he moved over to the Far Ultraviolet Spectroscopic Explorer, also called FUSE, working in, as you can see, in ultraviolet. And now he has moved to infrared. Most of his time is spent now on the James Webb Space Telescope. And I don't know what else to say. He's a really great guy. I think you're going to enjoy his talk tonight. Ladies and gentlemen, Dr. Bill Blair.
Thank you very much. It's a great pleasure to be here tonight to tell you about some research that I've been involved with. Most of my effort these days is functional work. I'm actually working to help the Institute prepare for the James Webb Telescope and prepare the ground system, it's called, the software and the systems that will support the James Webb Telescope and astronomers to propose for the James Webb Telescope. And so most of my effort is in meetings and that kind of stuff now, but I do have a bunch of good collaborators, and over the last 6 or 7 years, we're partway through a research project that I'll eventually get to tonight. I want to tell you some other things first before we get there. On this galaxy M83, and in the background here you see what is a large mosaic image from the Hubble telescope, one of the data sets that we took for this project to help us look at the star formation, huge amounts of star formation going on in here, and then find the supernova remnants, which is the stellar life, the birth and evolution of stars, and then the stellar death is the back end, the supernovae and the remnants, the things that they leave behind. And we try to study that galaxy and put it in context with our own Milky Way galaxy and other galaxies here in our local group, for instance. Okay, so before we get to the meat of things here with the star formation and the supernova remnants, I want to spend a couple minutes giving you some context and tell you about how we find the supernova remnants in other galaxies. We'll talk about what we see locally and what we're trying to find as we look farther away. And then we'll get into M83 itself and what we are finding and some ideas of what it might mean. So part of the context I like to do, I like to try to do a few things to make big numbers understandable. You know, we hear so much, you know, in the public domain these days, we hear millions and billions and trillions thrown around, and they're just big numbers. We just don't understand how big numbers really are. And in astronomy, of course, we have to deal with a lot of big numbers. We have the problem of distances. I mean, 1 light year, our yardstick that we use in astronomy, is some 6 trillion miles, 6 times 10 to the 12th, a 6 with 12 zeros, miles in 1 light year. And the nearest star is 4.3 light years away, but the distances to quasars and galaxies are millions or billions of light years. And so these are just big numbers. They kind of lose their context. The same thing with discussion in the public domain when we talk about budgets and this kind of thing. And I think part of the problem is, you know, we kind of hear million, billion, trillion, and we think they're kind of factors of 10 apart, but they're not. They're factors of 1,000 apart. You know, it's 1,000 millions make a billion, and 1,000 billions to make a trillion. Okay, so I thought I would just do a little exercise to give you some idea of how big a billion is. Okay, and so I have some props here. I have a ream of paper. I want you to use your imagination here a little bit. Okay, so the ream of paper has how many sheets of paper in a ream? Do you know? 500. 500 sheets. Okay, let's assume every sheet of paper in here is a $100 bill. Okay, so we got 500 $100 bills. That's $50,000 right there. Okay. So if I take 2 of those, we got $100,000. So that's a little easier to go by factors of 10 from, so there's $100,000, $100 bills side by side, and I got a yardstick here. That happens to be about 4 inches, okay? So 4 inches of paper is like $100,000. So 10 times that is $1 million, okay? If we had the stack of paper that high, that's a meter thick, 40 inches, that would be $1 million. So $100 bills stacked up to there is $1 million. $1 billion is 1,000 times that, a kilometer, 6/10 of a mile. Okay, so when you hear, so just to pick a random number out of the the news, 913 million. That's over half a mile high stack of $100 bills, folks. So that's a big number. Okay, big numbers. So let's do one more thing. Let's go one more step. Instead of money, let's talk about time, because time is another thing in astronomy that gets pretty hairy for us, and it's because there's such a dichotomy between our experience of time, where like 100 years is a long time to us, but to realize that 1 million years, or in some contexts, even 1 billion years in astronomy is considered a short time, because the universe itself is 13.8 billion years, and so you're looking at the evolution of galaxies from early times on. 1 billion years is really not that long. Believe it or not, right? So we could do that same thing. Let's take one sheet of paper, and this is now a timeline, okay? One sheet of paper is 100 years, a human lifetime, a long human lifetime, okay? Well then, 1 million years is that big, and 1 billion years is the 6/10 of a mile, 1 kilometer tall. So this is a short time in astronomy. One sheet of paper is a long time to us. And that's why we sometimes have a hard time communicating these big numbers. Well, so now we're going to look at star formation in M83. You collapse a cloud of gas and dust, it creates a whole bunch of stars. There are a whole range of different masses. The big massive stars only live for a few million years, short time, okay? Whereas, our sun, we know, is 4.5 billion years, is only maybe about halfway through its lifetime. So the low mass stars that form will stay around almost forever from an evolutionary standpoint, for the galaxy standpoint, whereas it's the most massive stars, the ones that live fast and die young, that create most of the energizing of the interstellar gas, forcing new star formation to happen as those shock waves from the supernovae impact clouds of gas and dust and make them collapse and so forth. So I'll probably mostly concentrate on the more massive stars and the supernova remnants that come from those massive stars as we go on through the talk. The other piece of context I wanted to give you is we all love these beautiful color pictures that we get out of Hubble and out of other missions as well, and I wanted to put that in context a little bit as well. This is the Kepler supernova remnant. It came from an explosion that Johannes Kepler observed in 1604. One of my favorite objects here, and what we're looking at in this color picture is actually a combination of Chandra X-ray data, 2 different colors here, blue and the green in this picture. This is harder X-rays that show you the outer rim is the brightest. That's the shock wave in the hardest X-rays. The green is a little bit interior to that. That is the actual ejecta, the star stuff from the supernova that exploded. Okay. The yellow, which I show in more detail on the other side here, but you see the yellow in here is the densest clumps of stuff. That's what Hubble sees, is the really dense stuff in the optical. So the yellow is Hubble, and this is 1 wavelength of infrared emission from the Spitzer Space Telescope. It's actually showing us warm dust that is heated by the shock wave. And you see how it's one-sided, how one side of the structure is really dominant in the heated dust. And it turns out, putting all this together, that this is telling us that the shock wave is running up a density gradient. It's denser up there in the upper right, and the dust is denser, and it's getting heated up by the shock wave as it impinges on that denser material. So again, looking at things at different wavelengths, one of the points here is that supernova remnants observe across the light spectrum, from X-ray all the way out to radio. I don't have radio on here, but they're strong radio sources as well, infrared, optical, ultraviolet, across the spectrum. They're very multi-wavelength. And so that's why I'm taking a multi-wavelength approach to look at this galaxy, M83. We have to look at different wavelengths to find the ones that are bright in X-ray versus the ones that are bright optically and so forth. Okay, so when we make these color pictures, everybody kind of knows this, but I just wanted to point out that, you know, if I make one image in red, one image in green, and one image in blue, then where things are bright in more than one band, you get different colors. Okay, if it's bright in the blue and the red, you get this kind of pinky magenta color. If it's bright in blue and green, you get that cyan color. And if it's bright in red and green, you get yellow. And so if I make a color image out of 3 different images of different wavelengths of light, or different data from different instruments like we just looked at from Chandra and from Hubble and so forth, you can compare the similarities and differences by looking at the colors where they're both bright. That's one of the tricks we play. And then over here, I just show that basically it's not an on-off thing like this. It basically, there's all kinds of gradation in the color that you get as you combine those in different amounts. So as we make color pictures, we can actually use that to diagnose what's going on if we understand what the images are that went into the pictures. Okay, so one of the problems that we have just looking locally, you say, why do we look at M83, look, 15 million light years away at another galaxy to find supernova remnants? We've got ones in our own galaxy that we can look at in great detail, and indeed we do. But part of the problem is that we have very few of these very young objects that we can look at and understand and kind of put together the big picture of what's going on. This is the Crab Nebula with Hubble, 3 different wavelengths of Hubble light put together into a color picture here. And this is the Cassiopeia A supernova remnant, which is a much more massive star that blew up in our galaxy. This is the same color coding that I had on that Kepler picture a minute ago, where the yellow is the Hubble and the red is the infrared band, and the blue and the green are the X-ray. And you can see how they all mess up there in this explosion, which is expanding at very high velocities, even some 300, 400 years after the explosion, still expanding at 10 or 12,000 kilometers per second. Interestingly enough, the Crab Nebula, almost 1,000 years old, and it's only expanding at 1,800 kilometers per second, and we think it came from a much lower mass star. So let's say we have half a dozen of these kinds of objects or something like that to look at. We've got the mass varying, we've got the expansion, the age is different, the expansion velocities are different. How do we take all these pieces of information and put it together into a picture when we have so few objects to kind of put together and make that picture? And just as another sign of how crazy these are, this 8 or 10 solar mass star, we know, produced this crazy Crab Nebula pulsar down here in the center of the object that is actually what's energizing and actually accelerating the expansion of the material from the explosion. Whereas this big monster 25 solar mass star that blew up here made this wimpy little neutron star down here that we don't even see any pulses from. So there is a stellar remnant left behind from the explosion, but it's not anything that would knock your socks off like the Crab Nebula pulsar. So very few objects to understand the parameter space, and many things changing. It makes it hard. And so we'd like to find a lot of these young remnants and look at them, especially if they were all at the same distance. You take the distance difference out of it, you can look at that sample of objects that are all at the same distance and understand systematically what's going on with massive star supernova remnants. So that was one of the motivations for going to M83. All right, so I'm going to leave the Crab Nebula behind now. That's kind of at the lower end of a massive star. These are 3 supernova remnants of we think, very massive stars. Here's Cass A again in our galaxy, and below here I just have a blow-up of some Hubble data that shows some of the detail in this stuff. This is star stuff. This is the guts of the massive star that blew up, and the material is still in the process of flying out into space at very high velocities. And eventually it will blend back into the interstellar medium and maybe participate in the next round of star formation that will have higher abundances than the current ones do. Okay? This is an object in the Small Magellanic Cloud that is very similar to this, only it's larger, it's older, but the only thing we see with Hubble, this blue stuff that you see in that picture, is almost pure oxygen. It's from the layer of the star that produced oxygen. If you took a spectrum of that, you would see there would be some neon and some other things in there, but you see no hydrogen. It's all the star stuff that's flying out into space. This object is in the Large Magellanic Cloud, a neighboring galaxy of ours, and it is larger. It has a kind of an outer shell here that's starting to form from the blast wave going out into space and starting to sweep up surrounding material. So you're getting that outer shell starting to form. But down in the center here, this blue and green stuff in this picture is this kind of stuff. It's the star stuff, still visible, even though it's a much, much older object. And to put those three in a little more of a context for you, in this graph, I try to show you their relative sizes to give you a little sense. So Cas A, 340 years since the explosion, 18 light years in size. EO 102, this one with the phone book name, is about 1,200 years old and is a little over 40 kilometers per second. This is expanding at, say, 10,000. This is 2,000. And over here, the outer structure is not expanding rapidly, but that green stuff, the oxygen stuff in there, is still expanding at 1,000 kilometers per second, even some 3,000 years or more after the explosion. And so if we wanted to find this kind of object in other galaxies, we would want to look for high velocities, and we would want to look for these funny abundances compared to the surrounding gas. And that's one of the ways we try to find them. And just taking that one step further, I like to make this point because this is thought of as a young object. The Veil Nebula, the Cygnus Loop, is thought of as kind of an older, a middle-aged object, and yet this is the relative sizes again, not too different. 88 light years versus 82 light years in size. Again, this outer shell is thought to be sort of the wall of a cavity that was blown by the wind from the star before it blew up. So there's a cavity that it's expanding into. That's the same model we have for the Cygnus Loop. This bright emission on the outside edges where the shock wave is finally starting to hit the outside edges of a cavity. So the two stars that blew up here could be very similar to each other, and yet we don't see the oxygen-rich, the ejecta in this one. They're starting to tease it out of very deep X-ray observations of the Cygnus Loop. They're starting to see some of that enhancement. But most of that stuff is blended back in or faded away at this point. And so this object is on its way to becoming something like the Cygnus Loop, and they're about the same size. This has nothing to do with the rest of the talk, but I had to throw it in here. You see this little white box on the side. There was this wonderful picture of the Cygnus Loop, just that tiny little section that was released last year. That makes the point also that you use the different colors to represent things. So we've got an oxygen, a hydrogen, and a sulfur band in blue, red, and green. And then you can see how the colors are mixing together. You get the yellows, which means that the H alpha and the sulfur 2 are bright. You see places where the blue is dominant, where the oxygen, high ionization oxygen is dominant, and so forth. So you get some sense for how you get diagnostic power out of the color images if you understand something about what's gone into the picture. But that's just a spectacular picture. This cloud up here is probably unrelated directly to this. It's either in the foreground or background. It just happens to be in the frame here. And there's a one light year bar across there. So the whole object, of course, is much larger. We're looking at a tiny little piece of it. And this Hubble picture, is 18 orbits of Hubble data, about 100 separate images in those different filters, all aligned and put together. This was actually 3 by 2 with C3 fields of view for the Hubble telescope. So this has been all stitched together for six fields of the wide field camera to put together this picture of that one little piece of the Cygnus Loop. Hubble's job is to look at small areas of the sky in very great detail. That's its reason for existence, basically. Okay, well, we're almost to M83. I just want to kind of give you the big picture here first. I mean, the idea, remember, is that we want to understand the star formation processes and the whole evolution of stars, and we want to do that for galaxies in the local universe. It turns out M83 is a prime testing ground for doing this, because you want to understand, by comparing local galaxies to more distant galaxies, whether these processes that guide this stuff are universal processes or whether there are differences. And the part that I'm really most interested in and most involved in is in finding the supernova remnants, which is just the one part of this bigger picture. So most of the rest of this I'm going to be talking about trying to find the supernova remnants and telling you how we do that. So here's a ground-based picture, very nice ground-based picture of M83, about 15 million light years away. 1 arc second is about 72 light years. And 1 arc second is kind of, as you're a lot of amateur astronomers out here, I presume, or people that know that's basically kind of what you get from ground-based observations is about 1 arc second, or sometimes a little bit worse, sometimes a little bit better. But of course, Hubble can do about 20 times better than that. So we're getting down to just a few light years type resolution with Hubble pictures. When we look at this thing, that's 15 million light years away. And we can still resolve things at just a few light years in size. That's pretty spectacular. Okay, it's called a barred spiral galaxy. There's certainly other galaxies that have more prominent bars, but you can see it's kind of extended here. It's got this very bright nucleus where star formation is just happening in a tremendous burst. But you see also a lot of these H2 regions around out through the spiral arms where star formation is happening. It turns out this galaxy is a great place to look for supernova remnants because it's produced a ton of supernovae. We've actually seen over the last 100 years 6 supernovae in M83. We found another object that I'll mention briefly as we go along that has to be less than 100 years old that was probably a supernova that we did not see. Maybe it happened when M83 was behind the sun. We don't know exactly. But anyway, there's another one that's young. So probably 7 of them in the last century. Interestingly enough, none since 1983. We are due. We are due. We had 7 of them in the first part of the 20th century, and now none since 1983. So we ought to be seeing some supernovae coming from M83 pretty soon. And just for context, again, this is a 1/4 of a degree field of view that I'm showing here. Of course, the full moon is about a 1/2 degree across, so it's a sizable galaxy on the sky. But interestingly enough, if you put this where the Milky Way is, this whole thing is, you like put 2 side by side and 2 up and down. That would be about the size of the Milky Way galaxy. So it's actually a relatively small spiral galaxy compared to our Milky Way. I mentioned that it had 6 or possibly 7 supernovae. Here's where they are located across the galaxy. Some of them are very close to star-forming regions. Some of them are not. One is right down here in this bright nucleus where there's tremendous activity going on. Near star formation, again, near star formation up here. I'll talk about this object and this object. This is the one that I think we found that has to be young, but the supernova was not seen. But the point is, with this many supernovae, less than 100 years old, if we want to take, what do you want to take, 1,000 or 1,500 years as a young supernova remnant, there ought to be 60, 70, maybe even 100 of these young ejecta-dominated supernova remnants in this galaxy. And so that's why one of the reasons we wanted to look here. We also wanted to find the normal supernova remnants like the Cygnus loop, and so the search actually looked for both of those things. So just very briefly, we used a large ground-based telescope here at Las Campanas Observatory for a ground-based search, and we actually found 225 supernova remnant candidates from that ground-based search. So the question is, why do we need Hubble? Well, we could find them, but we couldn't measure their sizes from the ground. Even with very excellent ground-based data, most of the objects we wanted to get, see if they had shells or if they were very small objects or whatever, we couldn't do with Magellan, and so we had to do that with Hubble. And so down here is the Hubble part of the project. We also have 730 kiloseconds, that's a lot of time, on the Chandra X-ray Observatory to take a very deep X-ray picture of this galaxy. We found 440 point sources and lots of diffuse emission. I'll show you that. And then there are other data sets that we're working on, including radio, again, multi-wavelength, spectroscopic follow-up, and I'll show you a couple of spectra from that as we go along, but I basically won't talk about those very much, that part of it. So there is, I showed you here the optical picture of the galaxy, right? And here is this deep X-ray picture of the galaxy to approximately the same scale. You can even kind of see the spiral arms and that red diffuse gas there. You see this incredible X-ray bright region associated with the starburst nucleus in there, and all these little point sources. And the vast majority of those point sources are actually in M83. A lot of the brighter whitish looking ones are X-ray binary stars. And you can see that because some of those sources vary over time and whatnot because they're in binary orbits. And the things that don't look too impressive on here, a lot of these little red dots or yellow dots in places oftentimes are associated with optical supernova remnants. So we have a lot of supernovae that show up. The color coding here goes from relatively low energy X-rays in the red up to the higher energy X-rays in the blue. And so this diffuse gas, this is the brightest diffuse X-ray emission that we have seen in any spiral galaxy, by the way. So if it doesn't look too impressive to you, you should see some of the other galaxies. This looks pretty good. Just that tells us that there is hot, low-density gas permeating the spiral arms of this galaxy, and that has been energized by the stellar formation, the winds from the stars, and the supernova explosions over time have energized the interstellar medium of this galaxy, and we get this incredible bright diffuse emission. Also, just a little blow up and rescaled so that it's not burned out. This nuclear region has a tremendous number of point sources and diffuse emission in there as well. It's a very complicated region. Some of those, again, are aligned with supernova remnants, and other ones are X-ray binaries in that very active nucleus. But it's so confused in there, we've mostly set that aside and worked on the outer part of the galaxy. The big picture here is that M83, although it's hanging out there and looks like a nice big bright spiral galaxy all by itself, is actually much more extended than we give it credit for. This is the part we've been looking at here, the bright part. This is GALEX ultraviolet images, and the red in this picture is actually radio H1 emission, hydrogen emission, that shows that there is very faint diffuse gas way out there, and the blue light that you see way out here is star formation that is actually happening way out here away from the bright part of the galaxy. This probably indicates that at some point in the not too distant past, M83 had an interaction with another galaxy, and we don't see that other galaxy right now, but it was enough to kind of really disturb the outer structure of M83, and maybe what triggered this big burst of star formation in the galaxy itself. So that's a much larger scale picture than what we were looking at before. Okay, so how do we find supernova remnants? These are spectra. Aren't they beautiful? People like rainbows for spectra. For an astronomer, a graph of intensity versus wavelength or versus color, blue to red. In this case, these are optical spectra. Intensity, these are spectra to an astronomer. And what you see here, you see some low-level noise going across here, but then you see these spikes that go up. This is called an emission line spectrum. If you look at a gas cloud, an H2 region, or a supernova remnant, you see emission lines, these spikes in the spectrum. Okay, and the relative intensities of the spikes change as you look at different objects, as you look at different kinds of objects. Okay, so this is a shock-heated supernova remnant, and what you see is that this little line of sulfur out here is much stronger relative to the hydrogen, and there's actually nitrogen lines here right next to it. The sulfur 2 jumps up. These sulfur lines jump way up. The oxygen lines in M83 get very strong in many supernova remnants, not all of them, whereas in the starlight ionized gas, the oxygen is very weak, the sulfur is very weak. So knowing what the spectra look like, now I want to say, let's go and take pictures, and we're going to take little filters that just get the light from pieces of the spectrum, and we're going to take pictures, and then we're going to do an RGB of these filters and look for color combinations that will tell us which objects have strong sulfur 2. Okay, and that's how we find the supernova remnants. For the ejecta dominated guys, it's a little bit different. This is a spectrum, an integrated spectrum of Cas A in our galaxy. First thing you notice, of course, is the lines are huge, broad lines. That's from that high velocity of the ejecta still moving. They aren't all that broad, but they don't have to be that broad for us to see it. They just have to be broader than we see in these kind of spectra. So if you saw these things broadened, you would know that you had high velocity. Cas A, okay, so here's my oxygen filter. Here's my H-alpha filter. There's almost no H-alpha, and some of what's there is not really related to Cas A. And then there's a sulfur 2 filter here. So this object would look bright in oxygen, bright in sulfur, and almost no H-alpha. Or some of the oxygen-rich remnants don't have sulfur either, so that would be bright here and not much in either of those two bands. And so if I found things, if I color-coded this blue, let's say, then things that look really blue ought to be dominated by the O3 emission. So that's how we find the ejecta-dominated guys, or we try to. We can get confused with just the optical data here because planetary nebulae from low-mass stars also can have strong oxygen 3. And so the other thing we need is, like Cas A, we know we have this really strong soft X-ray emission as well. So we need to see something that's bright in oxygen and has an associated X-ray source, and then we're pretty sure that we've got an ejecta-dominated remnant. Otherwise, it may just be a planetary nebula. So here's the trick, all right? We put H-alpha in red, we put oxygen 3 in blue, and we put the sulfur 2 in green. Now, the sulfur 2 line is actually in the red part of the spectrum, but if I did red, red, and blue, I don't have any diagnostic power, right? So I made the sulfur 2 green, and now things that are yellow are strong in sulfur 2 and H-alpha. Those are the normal remnants. If I find things that are blue or in the cyan, I'm pretty sure that I've got something that might be the ejecta-dominated thing, and that's the trick that we play. And so here's a little example, and I'm showing you the black and white images individually first, and then here's the color image down here that I'll get to in a second. So the trick also is that when we take images in these emission line filters, you also get some starlight. And so you take a picture that just gets the stars, and you scale that and subtract it away so that you get a pure emission line image. So here, except for maybe a few little stellar residuals like this, this is the oxygen 3 emission only. Here's the H-alpha emission only, and here's the sulfur 2. And you can do ratios in black and white, and you can find things, right? Like here's the ratio of sulfur 2 to H-alpha, and there's kind of three regions that pop out here. And it turns out, here they are in sulfur 2. There they are in H-alpha. This was pretty confused, but these two, you can see they're about the same brightness in sulfur 2 and H-alpha, and sure enough, they pop out in the ratio. What's really neat here is that even though there's all this photoionized gas around the region, you can still pull out in the ratio that there's actually something with enhanced ratio buried in that H2 region. So there's 3 supernova remnants right there. You could look at the O3, and here's these two actually happen to be fairly strong in oxygen 3 as well compared to H-alpha. And so let's look at the color picture. The ones that are bright in all 3 are kind of whitish or even a little bluish because they've got so much of that oxygen emission. But we already looked at the ratio of the sulfur 2 to H-alpha. We know those are high. This guy does not have very much O3, and so it comes out looking kind of greenish yellow, combination of the H-alpha and the sulfur 2. So that all kind of hangs together. So you say, wow, look at that guy. There's a nice bright, possibly oxygen-dominated supernova remnant, right? Well, it turns out that's a planetary nebula in M83. There's no X-ray emission associated with that, and so that was a close but no cigar in that case. So with Hubble, what we do is we go and we get the size of these guys, and then we actually find some additional objects as well, because in those confused regions at ground-based resolution you can't find them, and sometimes to Hubble that they pop out. So here are 7 fields of Hubble data with C3. These 2 green ones were actually taken shortly after the last servicing mission when the camera was first installed, and then I came back with a team and we got these other 5 fields to kind of round out the coverage and get most of the galaxy. And we looked at it with a bunch of continuum filters, the star filters, and then we looked at it with a bunch of these emission line filters and played this game over that whole galaxy. And that's what it looks like when you stitch it all together. And thanks to Zsolt Levay here at the Institute for putting that pretty version of it together, but also thanks to a couple of folks here, Jennifer Mack and Derek Hammer, who were the ones that figured out all the alignments and all the tweaks to get it all lined up properly so that Zsolt could work his magic on that picture. And if it looks sort of familiar to you, but not that familiar to you, well, if you kind of cut off this little wing out here and just made a nice rectangle out of that and turned it around sideways, you'd get this nice picture of the version that was put out as a press release back in January 2014. That's the same data set, scaled a little bit differently, shows the stars a little bit more dramatically, and so forth. But that's a pretty famous Hubble picture now, and it's the same data set that I'll be talking about. So it's nice to look at the beautiful picture of the whole galaxy like this, but the real power of Hubble is when you start zooming into it where you can see the details. And here are a couple of, this is still a very large area, 5,000 light years across, showing dust lanes, the star formation going on in here. This is a little closer in toward the nucleus. You can tell from the background, and you can just see the tremendous dust lanes and stuff in this galaxy. But behind that, these tremendous regions of star formation also going on. The red regions, of course, are where hydrogen gas is being ionized by the starlight. That only happens for the first maybe 5 million years after a burst of star formation, maybe 10 million years on the outside edge, and you lose that H-alpha emission, and it leaves behind the stars, and it might look something like this. Very young star-forming regions, very compact and condensed. You can see that there's bright light in there, lots of stars that are not even resolved, forming, but they're ionizing the gas around them. Then maybe a little longer along the way, that cluster of stars has had enough time, the stellar winds and a few supernovae have started to blow a bubble, and they're starting to move that stuff away from the site of star formation. And then maybe 50, 70 million years later, that material has all been dispersed, and you're left with a cluster of still fairly young stars. But you see there's a lot more red dots in here. Those are red giant stars, some of the more massive stars that have now started to evolve away from being blue and become red giant stars. So you can actually look at the stellar component and understand a lot about what's happening with star formation. Interestingly enough, we don't find supernovae in places like this. Now, it's partly because supernova remnants, we don't find them in regions like this because the gas has all been cleared out. If you blow something up in there, it just expands out and it doesn't hit anything, so it never gets bright. So we no doubt are missing some supernova remnants that happen in that scenario, but we tend to find supernova remnants in regions around regions like this. And so for instance, here is one example, and I'll just real briefly tell you, I'm not going to talk about this in any detail, but there's an infrared iron 2 line that Hubble's infrared channel can observe that turns out to be a very nice diagnostic for shock-heated gas. In this case, we're losing the data up there, but you can see that this H2 region that's associated up here just is not there at all in iron 2, and this little dot here is. That's a clue. White means it's strong in all 3 of my bands, right? It's not an oxygen-dominated guy, but it's bright in all 3 bands, whereas that photoionized stuff is not, and so that's a clue. And it's very tiny. This, I don't have it marked on here, but that circle is 3 arc seconds across, so that's way below 1 arc second in size, that little dot. There's no star there, so it's not a subtraction problem or anything like that, and it's a strong soft X-ray source. So that is a young supernova remnant in M83. Doesn't look like much, but some of them are a little more extended. Here's a little region of M83 where there's 5 of them in one small region. And so some of these guys, this is the emission line band over here. You can see little shell shapes to these guys and whatnot, so they're resolved. This one's a little more funky up here. All of them are bright in iron, which is nice to see. As a matter of fact, here's one that's bright in iron that we don't see optically. We don't see an X-ray. And it's because it's against this dark lane. It's probably behind the dust, and this infrared line actually gets through the dust. And so we're finding ones that we would miss otherwise because we've got that iron picture as part of the thing. So there's 5 supernova remnants, one that was not known before, and here we can now come in and measure the sizes of those guys and actually use that to understand the evolution. So I like to show this one because this is basically a Cygnus loop. A big, 70, 80 light year across object. You can see the shell is resolved there. It's strong in iron 2. There's some stars in the region, but nothing that would contaminate it that badly. And it's a strong soft X-ray source. I have a spectrum of this one. Here's the oxygen lines and the hydrogen line that's in the blue part of the spectrum. And then this is the red part of the spectrum. You can see the strong sulfur lines compared to hydrogen and nitrogen. Just what you like to see. And again, no evidence of broadening above the instrumental profile in the spectrum. So that's a Cygnus loop in M83, 15 million light years away. So we'll come back to the young remnants in a minute, but I wanted to talk about the historical supernovae again for a minute. And in particular, this object, 1957D, so that's a supernova that was observed in 1957. So we know how old that one is. And then this object down here that we found that I think is comparable in some ways to, well, it's definitely a young supernova, and then in some ways it's similar, in some ways it's different from 57D. So here's a couple of pictures. This is the Chandra X-ray picture. In this case, it's a blue hard X-ray source, which is not typical for supernova remnants. They're usually these red colors. That might mean it's got a pulsar in it, because pulsars have a different kind of X-ray spectrum. Okay? At ground-based resolution, this is what it looked like. There was a blue dot, oxygen, blue dot, and it had some red stuff next to it, but we really couldn't see what was going on. And so these two now are the Hubble pictures that have been zoomed in to that little yellow circle up there, so we're just looking at that region. And sure enough, what do we see? Blue, dominated by oxygen 3, that's the 57D, and here's some H-alpha emission that's associated nearby, but is not part of that structure that we see there. And so that should show broad oxygen lines if we know what we're doing. And sure enough, in the spectra, here we have the oxygen line, and it's very, very broad. Interestingly enough, from 1989 to 2011, when we got the last spectrum, it has actually faded quite a bit, but it's still there, still broad lines. It's associated with a little cluster of stars. This is Hubble data as well of the stars. And we can actually go in and do photometry for those stars and understand what the most massive stars that are in that cluster are. And the most massive stars are about 17 times the mass of the sun. So if this one blew up, it had to be more massive than that, because the more massive they are, the faster they go through their life cycle and blow up. So it tells us, it confirms basically that this had to be a massive star that blew up. So that's the 57D guy. This other one, just take a minute to explain. These are ground-based pictures. This is the Hubble pictures zoomed in again, so the scale changes between those two. And here's the spectrum of that object that we found after the fact. The story goes like this. We found this object in our ground-based data. We actually thought that it was a larger object and that this was a bright knot maybe on one side of the shell there. But when we looked at the X-ray data really seemed to line up with that bright dot up there. And so we came in with a spectrograph and took a spectrum of that dot, and this is what it looked like. And it's very broad lines, very high expansion velocity, so it's a young object. And the reason we found this with our three little filters, right? I put an H-alpha narrow filter there and a sulfur-2 filter there, and it looked like it was strong, and sulfur-2 to H-alpha, and yet it's got this huge feature that goes over that entire region of the spectrum. So I just got lucky on that one, and it does have the oxygen as well. So we found it as an interesting object, but we didn't know that it was had this high velocity until we got the spectrum of it. Well, now we bring Hubble into the picture, because Hubble can see the bright knot, and it actually can't detect the low surface brightness stuff adjacent to it there. But here's H-alpha, sulfur-2, O3, just like, you know, filters got it, and but it's very, very tiny. It's just a dot. It looks like a star. It's unresolved. It's very tiny. So from the upper limit on the size of the object and the expansion velocity that we got from the spectrum, we can say that it has to be less than 100 years old. So this is the one that we think is a young supernova remnant where the supernova was not observed. Well, okay, so we're trying to find these young guys, and what did we find? Well, if we just look at the sizes of them, the ones that are less than 35 light years, 11 parsecs, forgot to change that, sorry, size, we found about the right number of objects. We've got 60 objects that are about the right size, that are tiny little supernova remnants. A number of them are X-ray sources as well. But only those two objects that I showed you, and one more that I'll show you in a minute, that looked anything like we expected for those ejecta-dominated objects. What do the rest of them look like? Well, they look like this, kind of like that one I showed you a minute ago. Here's another one. A tiny little dot, white, right in all three bands, not dominated by blue, by the oxygen. Strong iron source, strong soft X-ray source. There's a few stars in the neighborhood, fairly blue stars, so one of them blew up. And we take the spectrum. No high velocities. This object is the size of Cassiopeia A, and yet it has no high velocity material. And its spectrum looks like the Cygnus loop, or the other ejecta, or not, the other ISM dominated spectra, the normal supernova remnants. It does not show evidence of being ejecta dominated. So where are all the Cas A's? This is the third object that has some hope of being a Cas A. We don't have a spectrum of this one yet, but again, in oxygen, and there's no star right there. It's right on the edge of the bright nucleus of the galaxy. That right over here is the bright, bright nucleus of the galaxy, so this is right on the edge. This guy, magenta colored, means it's bright in H-alpha and O3. It's not what we expect exactly, but it does have the strong O3, and it's very compact and there's no star there. So I think if we get a spectrum of this, that we have some hope of maybe seeing high velocities in that one. So that's the third one that's kind of like Cas A. But we're not finding 60 or 100 of these things like we expected. And we found the young ones, and they don't look like this. So here's what's going on, apparently. We're not seeing counterparts to these local ones that we've seen, where they get this big and still show evidence of high velocity and ejecta-dominated. We're seeing things the size of Cas A or the Crab that already look like the Cygnus loop, that have evolved beyond the ejecta-dominated phase into this phase where you're looking at shocked interstellar gas surrounding the object. So the supernova remnants in M83 are evolving very quickly beyond the ejecta phase and into what's called the radiative phase of evolution. So we didn't find what we expected to find, and these cards will be on sale in the lobby if you want to buy one and send it to me after the meeting, because sometimes it doesn't work out the way you expect it to work out, But so I guess this is probably the most appropriate one for my situation, if you. But when science gives you lemons, well, you make lemonade, right? And so we've learned a lot. We've learned some really interesting things about this galaxy. And a couple of things that I really didn't highlight to you too much. I'll do number 2 here first. Basically, M83 has very high chemical element abundances, even compared to the Milky Way. We had the small Magellanic Cloud, the large Magellanic Cloud, the Milky Way, and M83. The abundances go from about 0.2 times the sun's abundance to about 0.5 in the LMC to the Milky Way abundances. This galaxy has twice solar abundances over that entire galaxy, and probably even higher in the center. And I think those high abundances are part of the story. The other part of it is this X-ray data, remember, shows all this diffuse hot gas in the spiral arms. That's high density, high pressure gas in the interstellar medium of M83. So let's put these two things together. High chemical element abundances in a massive star allows the star to have a very strong wind that would blow material off before the star explodes. But if we've got a hot, high pressure ISM around it, that stuff can't go very far. It hangs out right around the outside of where the star is going to explode. So when the star explodes, it rams into that stuff very quickly, and you get a bright radiative supernova remnant very quickly at a small diameter. And so I think that's what's tricked us here. We're finding the young remnants, but we're not catching them in that ejecta-dominated phase that we were hoping to find. And it turns out this is very interesting, and we're still trying to piece together models and things that would help us understand exactly how that all transpires. But that's our working model for what's going on. So, in summary, basically, we did find a lot of young supernova remnants, as we expected, but we did not find them to be in this ejecta-dominated state that we did expect, and I just talked about the reasons. I hope as we get additional spectra for some of these candidate objects that we might find a couple more of those young objects with the very broad lines like that one that I showed you. But that's no guarantee, and it's certainly not going to get us up to 100 of those young objects that way. So that's it, and thanks for listening. And this is just kind of showing you where all the supernova remnants are across the galaxy in the optical and the X-ray pictures. I'd be glad to try to answer some questions for you. Thank you very much. Yes, sir.
So you were saying that the density of the interstellar medium may have had an impact on the velocity. Since we're viewing this, like plan view and not edge view, are you able to also plot how deep into the center axis of the galaxy these various supernova are?
Only sort of indirectly. Like, for instance, that one that I said it was seen in iron and it wasn't seen in the other wavelengths, and that iron gets through the dust and it's sitting right on the dust lane. I know it must be behind the dust, but other than that, I don't really have depth into the galaxy information. That's very small distance compared to the distance from us to the galaxy, so it's just they're essentially all at the same distance from my perspective. But yeah, it would be hard to pin that down with any certainty. Yes, ma'am.
When you're looking at supernovae in the visual spectrum, it looks like it's just traces
In the actual supernova spectrum or in the remnants?
I remember you showed a photo earlier that actually had a space from the visual spectrum, and there was some material that was still just in the visible spectrum of light. I'm wondering what that is.
So from the supernova itself, basically from the ejecta. So the spectrum would tell me, and if the spectrum is emission lines, I could even get the composition of the material. And so, for instance, in Cas A, that yellow stuff in the Hubble picture there was dominated by oxygen and sulfur and argon and calcium emission. No hydrogen, no nitrogen. That's a clue right there that it's a massive star, because that's the kind of stuff you get from what's called oxygen burning and so forth. So but I could look at a different spot and I'd see a different spectrum and it would have a different composition. It came from a different layer of the star or whatever. Of course, as we go to M83 or larger distances, we can't see the individual knots like we see in Cas A, and so you get more of an ensemble spectrum instead. If I didn't answer your question, come up and I'll try again. Yes, sir.
When you were speaking of the age of the supernova and you talked about velocity, but wouldn't acceleration interplay with the time factor of the age?
It could in principle, although the vast majority of the core collapse remnants, now the Crab Nebula is different, I'll give you that, but most of them explode, they're flying out very rapidly, and then eventually they're going to slow down with expansion. They slow down with time, they don't accelerate. The Crab Nebula is different because it's got that active pulsar in there, and that pulsar, that spinning pulsar, you got a 1.4 solar mass object spinning 30 times a second. Mind-boggling. So the energy coming off of that in particles and magnetic fields and whatnot is what energizes that blue diffuse gas in the middle of the Crab Nebula. And that synchrotron, it's called synchrotron emission, that emission is actually pushing out on the filaments and accelerating them. And so they're actually going faster with time. Even though it's only going 1,800 kilometers per second compared to 10,000, that was must have been a low energy explosion or something that just didn't start it off that fast, but it's actually being accelerated, yeah. Now, but most of them, it's just boom, it goes off, they fly out, and eventually they slow down. Yeah, so for Cas A, for instance, interestingly enough, Cas A, this 340 plus or minus a few year object in our own galaxy, the supernova was not seen in roughly 1680. And here we've got the Chinese have observations that go back to, BC times, right? And somehow in 1680, even with European observers, and it was placed well in the northern sky and everything like that, they didn't see the supernova. Now maybe it was a subluminous supernova, but even so, it's in our galaxy. It should have been easily visible, probably. But to get the age of it, they look at the fastest material they see flying out right now, assume that's undecelerated, and look at its proper motion, and then they take that backwards in time, and that's how they came up with the 1680 number for that one. Yeah. Yep.
All right, we've got a question from the online folks. Let's see. Given that it is difficult to determine supernova remnants from type 1A supernovae versus core collapse, how does that uncertainty play into the star formation calculations or other information? So the idea is you were looking at it, you showed a lot in the spectra that you're, almost sort of a case-by-case basis, you have to figure out what the progenitor was. But
right.
How does that play into the star formation rate type calculations you want to do with this?
Yeah. So it's an area of ongoing research. Basically, once the objects have expanded to the point that they're just shocking the interstellar gas around them and expanding, you can't tell what kind of a star it was that blew up without knowledge of the supernova itself. But you can play some games. You can say, wow, here's the supernova remnant. It's right next to this big cluster of blue massive stars. Probably a core collapse, even if you didn't see the supernova, right? And then taking it the other way, when you see a supernova remnant that's kind of out in the middle of nowhere, and there's no young star cluster around or anything like that, you could say that was probably a type 1A, exploding white dwarf, type 1A supernova. There's different types of supernovae. And so you can look at an ensemble in a galaxy that's been done in M31 in particular, and they try to make those correlations and try to look at those subsets separate from each other and see if they can find correlations and stuff like that. But it's an uncertain business if you haven't seen the supernova.
Yep.
Yep.
Other questions? Check online.
I wore them down.
Let me check online to see if there's any more online. Yeah, you've already answered the question about how you determine the age of supernova remnant. All right.
Years ago, they were always saying these objects in space were ice balls, just plain ice. Now, all of a sudden, you're telling us that there's iron and things in them, which is what was observed by, say, Jim Mechanics' class back in Cornell years. But now, we landed on one and we drilled it, and it wasn't ice. So now we've got more of these things that are more metals than say, snowballs.
Well, they're mostly, the comets are mostly ice. They have an admixture. It's just basically whatever came together to make the object, right? So what, depending on what part of the solar system they formed and what the materials were around when they formed, they have different admixture of ices versus rocky, dusty stuff. You know, there's a lot. We look at stars that are forming planets right now, and they have disks of dust and gas around them. That's the stuff that some of which ends up making comets, right? And so it's a mixture of gas and dust, and you just get different comets will have a slightly different mixture of those. Temperature would be a big factor, yeah.
Right. Well, also you recognize that if you examine the surface of a comet, you're not going to find a lot of fresh ice because as it goes past, those volatiles will go away on the surface of the comet. So the part of the idea of the deep impact mission was to try and look at the subsurface material that spews out when we basically threw a washing machine into a comet at 25,000 miles an hour, if I remember my analogy. Yeah.
Yeah.
Right. Okay, is there somebody from the Maryland Space Grant Observatory here to take people across the street? I do not see that person. I will talk to them next month and make sure that they either show up or let me know with an email. Let's see, next month we have Toby Mariage talking about the Cosmology Large Angular Scale Survey, and that will be on November 1st. All right, that is a week before Election Day, so you know you won't have to deal with any of the election stuff that night. Hopefully, maybe we'll have to deal with the Orioles. I wouldn't mind if that happened. But ladies and gentlemen, let's give Bill one more hand. All right. Did anybody leave a thermal cup? The facilities found this 2 months ago, I think in August. And then they handed it to me last month after the talk and said, "Oh, we
Door
found this
prize,
out."
door prize.
Yeah, so door
we'll have a
prize.
drawing.
Ask the best question. No. If you, and this is yours, come play. All right. Thank you.
You're welcome. Hope that was about what you wanted.
That's great. And the multi-wavelength aspect of it, in terms of you showing all of the various filters that you used and such, and the ways you try to study cosmology. All right. In December, Christine Chen will be talking about debris disks and the evolution of planetary systems. Yet another one of the hot topics in astronomy, talking about extrasolar planets and how planetary systems develop. I mean, I remember when I was a wee lad, just an undergraduate, we knew nothing about how planetary systems develop, and the amount that we know now is just amazing. It's one of the great topics. Unfortunately, in January, we have our favorite speaker, TBA, because it's hard to get somebody just after New Year's. I wanted to ask a question, folks. Would you prefer that we delayed this until January 10th instead of January 3rd? Or would that not make a difference? Anybody think it would be good to delay? Anybody okay with? Everybody would just think the 3rd is better? And who doesn't really care? Okay. Overwhelming don't care a little bit towards the January 10th, because the American Astronomical Society meets the first week of January, and I often have trouble getting speakers because half the institute is out at the conference. So I might consider delaying that. All right. The construction update. Hopefully you guys had to come a different way to get here. Hopefully, obviously you made it. Hopefully there isn't another 50 people out there getting lost. If so, hopefully they will find their way in. You have to come from the south because north of it is closed. Here is the map. This blue part is the stuff that's done. Looks real nice, especially this path along here. It's a really nice little path if you see it when you're during the daylight. But this yellow section here and this red section up denser, and it drops down into the deeper, warmer ice. Okay, and notice that they call this the convecting portion of the ice shell. All right, we sort of think of ice as rigid and fixed, but on Europa, there actually is motion through the ice, and they talk about it convecting, with the liquid ocean being underneath that ice layer. Again, how thick is this ice layer? We're not sure. So it shows there is at least motion in the ice on Europa, and there's water deep underneath, and the question is, well, how much of that water gets up near the surface? Because if we want to check for life in the universe, we need three things. We need energy, carbon, and water. That's what life as we know it requires. Well, energy and carbon are pretty easy to find. Water is really, really hard to find. So Europa, where we know there is some water, is a place to look to see if life could have developed, even microbial life, on Europa. All right? So we have actually seen water plumes on another moon. This is Saturn's moons Enceladus. By the way, this is Saturn's rings up here, okay? A nice edge-on view of the rings. And this is from the Cassini satellite, where you can see these plumes coming from Saturn's moon Enceladus, all right? And we've also seen indications of possible plumes on Europa from Hubble. Now, Hubble did not see water plumes. This was in 2012. What Hubble instead saw was auroral emissions from hydrogen and oxygen. What is water composed of? H2O, hydrogen and oxygen. So these are auroral emissions associated with Europa from hydrogen and oxygen, which are indicative that there might be water plumes. Here, those are now closed and will be through December, okay? So for the next several months, you'll have to approach from the south. It definitely has lengthened my commute. Our website with information is if you just take your favorite search engine and look for Hubble Public Talks, you'll find it. We have links to our live webcasting, both on YouTube and on the STSCI webcasting site. Our archives of the past lectures, again on YouTube and the STSCI webcasting, and a feature that has been used an awful lot because I get an email every time it is used, people signing up for our announcements. Thank you all for signing up. It makes my job a lot easier in getting the information out to people, not only around the Baltimore area, but across the country. We also, of course, have our list of upcoming lectures. So visit our website to find all that wonderful information. Announcements, well, just use our website because there is mail list at stsci.edu, but it's much more difficult. Just use our website. If you want to contact us, you can send an email to publiclecture@stsci.edu, ask comments or questions. We are also on social media, Facebook, 2 Twitter accounts, Google, Pinterest. I will note that my Hubble's Universe Unfiltered blog on Hubble site is getting updated more frequently. We have, it's the new fiscal year. The funding for this fiscal year has enabled me to put more time into my blog. I put up 3 posts last month. I also do Facebook, Google, and Twitter every now and then. I don't promise to be daily or at all on something like that. Observatory, I didn't check my email late this afternoon. The person from the observatory is obviously not here. Remind me to ask again. There is a really lovely science story behind it. So let me explain the science behind it, and you'll see how beautiful they really can be. So this is Jupiter's moon, Europa. It's the smallest of the 4 Galilean moons, okay? And we believe its interior structure has an iron core, metallic core. It has a, it has a rocky section, and then it has a liquid water ocean and an icy crust, okay? Due to various measurements in the magnetic field motion to it, we believe there is a liquid water ocean subsurface on Europa. The question is how thick is this ice layer? Is it 10 kilometers thick or is it 100 kilometers thick? We're not exactly sure. There are two camps that argue about this. But when we look at Europa's surface, this is Europa's surface, we see a modeled ice sea surface. And this is the famous ice rafts picture taken by the Galileo satellite, which looks a lot like the broken ice structures around the North Pole, okay, on Earth, indicating that there might be the same sort of motion of, perhaps not on top of a shallow water layer just underneath as we have here on Earth, but that there might be softer ice and there's some sort of motion, there's some breakup and motion through it, okay? We have evidence of motion or sort of ice tectonics on Europa, and it's something like this, where we've got these subsumption bands here. What we believe is happening is the cold outer ice shell is actually subducting, just like the plates subduct on Earth, subducting below another ice layer, all right? And so this is in at the end to see if they are here to take us up to the observatory tonight. Okay, and now news from the universe for October 2016. Our first story, lovely plumage on Europa. How many of you recognize the phrase lovely plumage? All right. Oh, not that many. Uh-oh. This isn't a reference for this audience. All right. This is from the Dead Parrot sketch of Monty Python's Flying Circus, where John Cleese's customer comes in to return a parrot that is dead, and Michael Palin, as the shop owner, tries to refuse to acknowledge that the parrot is dead, saying, "Oh, the Norwegian blue, lovely plumage." And just talks about how it is, it's just resting, it's pining for the fjords, and such. This is an extremely famous sketch amongst Monty Python fans, so much so that when Monty Python had a reunion in London, it was celebrated with a 50-foot dead parrot by the Tower Bridge. So lovely plumage has very little to do with this story. I just wanted to show this image. But the plumes on Europa are these. And they're not really quite so lovely to look at. Matter of fact, you may not even see them unless I put in the arrows, okay? All right, so this is an image of Europa from the Galileo mission. It's a mosaic put together. And these are the plumes down here in white. The background is from the Hubble STIS instrument, okay? And you're seeing this white stuff down here, and it's kind of pixelated and stuff. And I wouldn't call it lovely. They're kind of ratty, except